Good morning. My name is Steve Adler, and I work for IBM. And you're joining us this morning on a webinar to talk about the dynamics of climate change, understanding and influencing the planet's future, presented by Drew Jones from Climate Interactive. This is the first of an 8-part webinar series we're hosting to talk about how system dynamics is really changing the world. We want to present to you a whole host of really exciting system dynamics use cases to illustrate how to think about things in systemic terms, because earlier this year we started a standards process at OASIS for a technical specification called XMILE, or SMILE. And XMILE allows different system dynamics models to be reused, to be componentized, to be stored in libraries, to help modelers and business people take full advantage of systems thinking and system dynamics. But of course, a language is difficult for a lot of people to read, a technical language, an XML language. So rather than show you the language per se alone, we thought we'd show you some really exciting use case examples of what these models look like, who's using them, who's benefiting from them, and how you can benefit from them. So our first speaker is Drew Jones. Drew Jones is the co-founder and co-director of Climate Interactive. They're a think and do tank, as they say, that creates policy-oriented simulations for a variety of top leaders around the world. He's been trained in system dynamics modeling at Dartmouth and MIT. He's worked at the Rocky Mountain Institute and served dozens of clients ranging from CDC to Harley-Davidson to the US government. He's created a model which I think is really compelling and exciting, and I hope you do too. And with that, I would like to turn the mic over to Drew and ask Drew to teach us about climate change and system dynamics. Drew.
Great. Thank you, Steve. Hello, everybody. Pleasure to be here. I'm just pulling up my first slide, and I've just been scrolling through all the attendees. It's great to see so many familiar names, old friends, and folks I haven't met yet. Looking forward to talking to you for the next 20, 25 minutes before we turn back to a more broad discussion. Just one thing about the logistics. There are hundreds of people on the phone and on this webinar right now, and we really want this to be as interactive as possible. So the way that we can do that is everyone's on mute, and if you have a question, if you have an answer to one of the questions that I ask you, and I'm going to ask you some questions, please type them into your GoToWebinar control panel where it says questions. If you put it there, then Karim and Bob Eberline will read them and scan through them to get the answers that we're going to really need. So that's the way we're going to communicate. So please go ahead and use that way so that we can be in touch. So I'm with Climate Interactive, and I want to make these main points today in this webinar. The first of them is about system dynamics, and we see system dynamics modeling as a powerful method, particularly for improving thinking, accelerating learning, and driving action, particularly in the context of complex systems. That is, where cause and effect are distant in time and space. That's in a business, that's in a city, that's in an organism, that's in the whole global climate change challenge. So whatever scale you're working, we want to introduce this and build your knowledge in how to use this powerful method. The second area of insights and main points are around climate change. And the short version of our insights is action towards the results we need is urgent and possible. Urgent, we need to do it soon. Possible, we can actually do this. Our contribution that I'm going to focus on today is how to build shared understanding across difference. And this was between cultures, between different scales of action in the climate change world. But what's really relevant here in this idea about XMILE is building understanding and shared platforms across technical analysts who don't use the same modeling language or physical language or speaking language, but also in modeling can't share models. And that's why we're so excited about what Steve was talking before about XMILE as a cross-platform approach. So that's what I'm going to be focusing on. Stepping back a little bit, at Climate Interactive, we have 3 criteria that we use when we think about using system dynamics. There's so many analytic methods in the world. Why use this one? We need an urgent, important, pressing problem, something where someone's willing to make a different decision, and hopefully it's a burning question on some people's desks. The second is that it really lends itself to situations where there are misunderstandings about how things behave over time, that is dynamics, or system-wide interactions, where people clearly aren't understanding something about the complexity of the system. The dream, of course, is number 3, that we have a lot of data-rich, either past data and or future. So the question is, did that apply? And we found maybe 5 or 6 years ago that it really applied in this area of climate change. And what was going on in 2006, 2007 as we were figuring out how we could use the models that had been developed so far in our field, we noticed in the negotiations that the United Nations was pulling together. Think about this huge global problem. The UN said, we're going to pull all the countries of the world together in order to address climate change. And the way that looked is that all the countries were going to say, well, we're going to reduce our emissions. But what we heard was this quote: the delegates said their heads were spinning because they were trying to understand the science and the assumptions underlying all the proposals for emissions reduction. They all used different base years, different assumptions. How could we make any sense of them? And so we started gathering the world's first spreadsheet to say, what is everybody saying they're going to do? Australia said we're going to reduce our emissions 5% below 2000. China had different language, carbon intensity 45% below 2005. Brazil was focusing on deforestation. You put it all together, pretty confusing. So big problem, some misunderstanding and disagreement, and they had really no idea what all of this would add up to. The other criteria was a deep misunderstanding of the complexity. And John Sturman and Linda Booth Sweeney, who were part of our team in really conceptualizing this whole idea, had done some studies that said that people misunderstand what we call the bathtub dynamics, just the basic, how does the climate system behave? And I'm going to show you in a minute what that misunderstanding was about. So, and there was a lot of data. A lot of other people had built very big, geographically disaggregated models, that looked at the small grid areas around the world, but really they hadn't communicated a lot of those insights to policymakers. So we built a simulation, and this was built upon the work of Tom Fitteman. Tom Fitteman was a colleague of mine when I was at MIT, and had built his thesis model that he had built from 93 to 97. What we did at Climate Interactive is we broke it into 3 regions, and I'm showing you the very simplest version. Now, mind you, this is a model. If you like modeling, we can send you this model. There'll be information about how to get that. You'll get an email about if you want to have the model and play with it yourself. It's an open source model. There's also, if you're a user of these models, there's a 15-region version that we can give you for free. It's the version that the U.S. State Department, that the Chinese government uses. It's the official negotiator version. We can send you both of them. Let us know. This is the simple one I want to show as a demo. And what it really does is it helps you see how we tend to use these models. This is built in Vensim, and you can see on the left CO2 fossil fuel emissions from 3 parts of the world from 2000 to 2100. See the blue line? That's the developed world. US, EU, Japan, South Korea. Emissions are higher here in 2013, but not growing quite as quickly as the red line, which is growing more quickly. That's China, that's India, that's Brazil, Mexico, growing more quickly over time. And then here are some of the poorer countries of the world not growing as fast. We call them developing B. If all of this CO2 gets sent out into the air, into the atmosphere, then what we have is the accumulation of carbon dioxide, and therefore temperature goes up. So here's temperature rising and rising. You see the blue line on the right. The goal is to get that blue line all the way down to the green line, which would be a max increase of 2 degrees. Of course, there are uncertainty ranges around that we could show you. But for now, let's just play a quick game. I'm going to ask you guys, or you guys suggest, what year should we cap emissions globally as a first test? And what we'll be able to do is move the sliders at the bottom to see what the result would be. So type into the questions, what year should we see these emissions cap? So, and then Karim, and if you would check out what people are answering. So please type in there if you have a suggestion. And Karim, if you'd give me the middle point. Are you starting to see any answers, Karim?
Yeah, they're centered around 2040, I'd say.
Centered around 2040. Okay, so people are saying 2040. What I'm going to do is I'm going to move the slider, and so that's at the bottom. And as I move the slider back, what we're going to see is you're going to see things move. So say I have it out here at 2100. Notice that as I move the slider, what's happening is that the model, because of the magic of Synthesim, which Bob Eberlein created, he's on the phone right now, the model runs so fast that you're going to see it run all the equations, and then you see the result on the right where temperature changes. So here I'm moving it. Okay, I'm moving it back and forth. Let's see. So watch all the red, blue, and green lines on the left cap lower and lower. I'm moving it back to 2058, 2050. Here we are at 2040. So all these emissions grow and grow till 2040, and this is great. The blue line is much lower than the red line. We've shaved maybe a degree of temperature off, but we've only closed, what is that, about a third or a quarter of the gap? It's not quite enough. We're going to need to go a little bit sooner. So someone type in, what's an earlier year that someone typed in, Karim? You can see that it wasn't quite enough.
2020.
Okay, 2020. What if emissions grow and grow and grow until 2020, and then we cap? That would close a little bit over 50% of the temperature goal, temperature gap. And I want to switch over and show, for just 1 second, pause and consider how crazy that kind of feels. That we capped emissions. Emissions are flat starting in 7 years, and still temperature goes up. And to go another level, I'm going to switch over here to look at CO2. Carbon dioxide concentrations in the atmosphere. That is how much CO2 is in the atmosphere. That's this number you've heard about, trying to keep it below 350 parts per million. We're at 400. It's going up. So emissions are flat, and CO2 in the atmosphere is going up. How messed up is that? It's really confusing in our minds that this would be the case. And this is what Sturman and Linda Booth Sweeney were looking at, this counterintuitive insight. It's only with system dynamics and the system dynamics framing that you start to understand why. What you can see is a bit of what's going on. The red line is emissions that are flat. The removals, that is how much CO2 is coming out of the atmosphere and going into the oceans and into plants, is well below those emissions. If you think about it as a bathtub, so let's go back over here and look at it this way. The emissions you saw, that first line, is about double removals. So if you have a bathtub, double is going in what's going out. So imagine a bathtub, double going in what's going out, kind of like what you see the levels of water here. Concentrations in the atmosphere is the bathtub itself. If you have double in going what's going out, then you're going to have that concentrations going up. And if you cap it there, where still your emissions are above your removals, of course CO2 in the atmosphere keeps going up. But that's not what our brains would like to have happen or expect to have happen. We think if we cap emissions, then we cap CO2 in the atmosphere. And we have spent years, even working with policymakers in the climate space, are actually somewhat surprised by this and find that this framing is very helpful. So far with system dynamics, I want to show you how we're spanning from a very complex, high-order, nonlinear differential equation model. And I show you all the testing we've done to build confidence in it and all the complexity of it. But then we span all the way over to what we actually deliver to the world, which is often very simple analogies that will help people understand why what's going on is going on. So using that analogy, I'll go back over and we can look, and you can see that red line is the inflow on the left. The blue line on the left is the outflow. That's what's going in, and what's going in is more than what's going out. Therefore, over on the right, we see the blue line going up. We're accumulating more CO2 in the atmosphere. So that sends us back, what do we actually need to do? Certainly, capping in 2020 isn't enough. So what we need is we need to start reducing emissions. And I'm going to pick a year. We're going to say, let's just cap for another 7 years and then start reducing. And what we end up doing with policymakers is saying, well, what if we reduce at 1.5% a year, or 2, or 3, or 5, or 4? And you can start seeing all of the results on the right. And it starts leading us towards what it really takes. And we could create that kind of scenario. It's not just, of course, about CO2 from energy and from countries, but we also have deforestation. So I'm going to move another slider over here. And we can grow more trees. That would increase the removals. So we create this scenario where we've grown till 2020, cap for 7 years, and then start 3.5% per year reduction, which happens to be about how fast emissions dropped in France when they went towards nuclear energy using a different source. So it's possible to imagine 3.5% per year reduction in emissions. Combining it with deforestation and afforestation, the blue line's under the green. We've closed the gap. So it starts to point at what we use this for. We usually spend 2 hours going through what we just went through, where we lead people through the process of discovering for themselves what it takes, given this complex system, to meet whatever goal they have. And we can show lots of other results, et cetera, but I think I'd rather move on and show you some of the ways that we built confidence in this model, but also how we translate it into a form that could be used by others. So we built confidence first by grounding ourselves in the literature. So the model was based on the work of Tom Fiddiman, who's at Ventana Systems. And here's the structure of it. And of course, it looks a bit more complex when you get underneath the hood of the model, but really it's pretty understandable. It's really a lot like the bathtub. Here's the inside of the bathtub, the CO2 in the atmosphere. These emissions are the inflow to the bathtub, and actually the outflows, it goes to a bunch of places. CO2 travels into biomass or plants. It goes into humus and soils, and there's flux back and forth, and it gets shoved down into the ocean. The more CO2 there is, the more radiating forcing, that's basically heating of the earth. And there's several feedback processes that we had to model using other people's analysis of how strong those different balancing loops are and what are the proper parameters that dictate how it behaves over time. To build confidence, we also had a scientific review where we pulled together a bunch of top scientists, and they said, you know, the model is good enough for its purpose. It has a very different role from the very geographically disaggregated simulations that we use to build confidence. Those models results were published. Here's a graph of them. It shows various scenarios for the amount of warming and temperature. You can see that the yellow line is a lower scenario, the red line's a higher one. So we use the same inputs as those models, and we then compared our results to say, hey, when you kick that model, you get a certain result. If you kick ours in the same way, how close to the result they got is ours? And the circles that I'm now pulling up show how close we were to the median for what their results were. That's one of the key ways that we build confidence in a model like this. So you saw the challenge, all these different delegates not understanding the result of pledges, and also we know there's a core misunderstanding. So what happened was, really things came to a head in 2009 in Copenhagen, where the UN said, all these countries have made pledges, and they had a press conference to say, the pledges to the United Nations are good enough. But what we did was, said, well, wait a second, we're adding up all the pledges, we found different results, and we went around and showed lots of people, and people listened. We briefed John Holdren, who's the White House science advisor, 48 hours before President Obama arrived in Copenhagen. This is a picture of him meeting with those other folks in Copenhagen. The lead U.S. negotiator, Jonathan Pershing, presented our results in front of the UN several times and actually shaped the design of the model itself. And then John Kerry picked up the model and actually tried to carry a laptop with the model into the Oval Office to show President Obama. So he tried to bring the model in there. The aides said, no, you may not bring a laptop into the Oval Office, so he had to bring our PowerPoint deck, which was kind of encouraging. That he used it, but good lesson if you ever get to the Oval Office. We published things in a result that was accessible to many people, and that was the climate scoreboard. And what it does is it showed very simply, and this got 1 million hits over 6 weeks, showed very simply, if you add up all the pledges, you don't get business as usual, which was the yellow line, 4.8 degrees warming. You also don't get the goal, which is 1.5. You get a little closer to what you saw when we did the simulation, which was about 3.9, with this blue area being the error bars. So we show this result to the world, and the UN still held a meeting. And this is a leaked part of one of their documents. It says confidential initial draft, where this is a meeting where they said to all the delegates in Copenhagen, the pledges are enough. But someone stood up and said, no, I've seen the work of Climate Interactive. And they scribbled it down on a piece of paper. where they had the climate scoreboard that said, no, we're actually headed towards 3.9 degrees or 770 parts per million. Somebody leaked this document to the blogs. It caused a big mess in Copenhagen because all the delegates were saying, hey, the UN saying that pledges are on track. Climate Interactive and their work is saying that it's not. So we stayed up all night, did all this analysis, issued a press release, got the word out to all the different delegates, and very quickly it changed the messaging from the UN. They realized that they could not just have a good PR campaign to say the pledges were enough, but they accepted that they weren't, so they stopped. And what that sparked was a process for tracking pledges and the results using C-rolls, and now about 10 other models are doing what we were the first ones to do. So in this case, system dynamics ended up being the very accessible way to get to people that launched really a whole industry and sets of meetings in order to track what are the results of all the pledges that are going down. It also sparked a lot of other people wanting to translate this into different forms. And this is such an important message when it comes to XMILE, because we need to be communicating across difference here. The biggest one, of course, is perhaps the Western world and China, because so much of future emissions come from China. So their government came to us and said, could we build a version of C-Roads in Chinese? You're looking at the interface right now. I went over several times with Tom Fitteman. You can see a picture of us training people at Tsinghua University in the simulation programs and in this model. And this is us sitting with some of the other modelers from over there. So what we're trying to do is make it much easier across platforms, like what XMILE is doing, across language and culture, to have a shared understanding of the dynamics of important complex systems like this one. We put a version online. You can go play with this. Just go type CLearn into your browser, and you can go play with the same model that I just showed you. And there's schools around the world that are using this. And media, we had reporters using the results from our models in the International Herald Tribune and in the New York Times. Activists, this is 350.org, made a poster with what we made, and shown you a little bit more about the, I already showed you more about the scoreboard. Science museums picked up the model and put it in there. We have a mobile phone version that you can go to that's called Climate Pathways. Anyhow, putting it into multiple forms is another way that we really try to engage people. John Sturman at MIT and I have designed a role-playing exercise called World Climate, where we have business people on the left, students on the right. The people on the floor are the folks who are playing the poorest countries in the world. The people at the tables play the richest countries of the world. They always get a box of donuts or something like that to show their power that they have in this system. And I say, I'm Ban Ki-moon. You've got 17 minutes to sort out climate change. Give me a proposal, just like I was doing with you a minute ago. We end up using analogies a lot, and like I showed you with the bathtub. So stepping back just a little bit, I want to hit my main points, and then I'm going to turn it over to get some of the main, actually, let's not hit the main questions yet. The main points. Let's pause here, and Karim, what questions do you see that have come up so far that feel particularly germane before I, yeah.
So one question is, are you using the same models as the IPCC global climate change models?
Are we using the same models as the IPCC climate change models? So we compare our results to the IPCC models, which are really just models built by many other research universities. They're called general circulation models or integrated assessment models. So we compare our results of our model against theirs as one of the ways to inform, are we matching what other people think are the likely dynamics? Karim, other questions?
Great. Yes. So what about dealing with uncertainty, for example, climate sensitivity?
What a good question. One thing we love doing with system dynamics is it being transparent about the likely uncertainty in many parameters. For example, here's a scenario we were just looking at. And there's a big debate in the world with, and it sounds like this. If there is, say, a doubling of carbon dioxide in the atmosphere, how much will temperature go up? So scientists are writing papers and trying to determine what that is. And this latest study that just came out a couple weeks ago widens the range, particularly considered the possibility that maybe there won't be as much warming if we have a lot of carbon dioxide trapping heat in the atmosphere. So there's a lot of debate about that. We don't like to say, well, we've surveyed the literature and the answer is 3. We'll put 3 in there. That happens to be the number that's in there. But we also embrace the fact that it could be higher or lower. So here in the same page where you see all these different, these are policy variables. At the bottom it says climate sensitivity to 2x CO2. There's the number 3. But what we'll often do is we'll be sitting with policymakers and someone will say, well, so-and-so said it could be 2.5. So we say, okay, what would be the implication if it was 2.5? So here we are, and we slide that number down and say, well, let's see. If it were 2.5, did you notice the blue line? I'm going to move it again. Look at the blue line on the right. Temperature would be lower. So instead of going towards just below 2 degrees, it's a little bit less. Or what if it's higher? And we thought we were going to hit 2, but if that number is as high as 4, then we wouldn't hit 2. We would have a lower chance of 2 degrees. So one of the ways is that we open ourselves up to that, and also with other parameters. And you can see the other ones that are over here. The second is that oftentimes people will just want to see the results within a range. So this is the same temperature. The red line is the middle line, and then we believe that there's a 90% chance that the result will fall between the green and the blue line. So we'll show temperature sensitivity that way. Karim, another question?
Great. Thanks, Drew. Yeah, there's a question. There have been some recent studies looking at quantifying the influence of climate change on human conflict. Have you started to incorporate any of these aspects into the C-ROADS model?
Have we included the effect on conflict? Wow, what a good question. In this version, no. At Climate Interactive, the short answer is yes. And if you're interested in that, there's a whole set of projects. This is the Climate Interactive website. We call it Adaptation and Resilience. One of our team members is now doing a project in Kenya where you're looking at the effect of drought, and we're starting another one in the Congo on the effect, as you just said, in human conflict driven by natural resource issues such as climate-related drought. So you go here, you can see this project on Kenya. It's a really good question, but is not one that we directly include in a model like C-ROADS, but we'll build a separate model that's much more regionalized. Another one, Karim?
Great, thank you. There's another question here. Yes, one criticism of the IPCC is that it is very conservative with respect to positive reinforcing feedback loops. How has C-ROADS dealt?
What a good question. So as we all understand about how the world works, there are many reinforcing positive feedback loops or tipping points, such as the albedo effect. That is, you have a warmer Earth, you have a smaller polar ice cap. So the smaller polar ice cap means there's less reflectivity. Don't have as much ice that's bouncing light and heat back up into the atmosphere. And there are about 8 or 10 other loops that we like to explore because they're pretty important. We tried to include them explicitly in here and have found that the state of the science doesn't allow us to parameterize the strength of those loops to the point that we feel we can include it in this model. And if you believe those loops are stronger, that number I just showed you, this 3, should be up much more towards 4.5. If you think those loops are weak, you move it down here. So the simple way to capture it is by changing this climate sensitivity. Very good question. Karim, others?
Yes, Drew. Can you explain to us how you got the policymakers to believe in your model?
How did we get the policymakers to believe in our model? The main approaches that we took were to go to the people whom they respect in the field and have them review the model. So that was our scientific review board. So having the thumbs up from people like Bob Watson and Steve Schneider. The second was we iterated with the policymakers. So we went to them and they said, what do you need? What would be helpful to you? And they would say, we want you to change this. And this is probably version 323 of this model. And so what we found is that it was necessary to iterate, and constantly make changes in order to capture how they wanted to see the world. Not just the levers, but also what was included in the system. For example, those positive feedback loops. If we included them and the numbers seemed hokey, we pulled them out. Other good questions, Karim?
Yes, thank you for that. The next question is, does the model incorporate economic and financial effects for different policies?
Does the model include financial effects for different policies? No. I'm being a little blunt, and we're doing another model right now on Brazil. And for that one, the answer will be yes. I'm just going to pull that up. That's like another example. For Brazil En-ROADS, it's going to include, this is another an adaptation that only goes through 2050, and it's going to be important to include, in this case, financial effects.
Great. How does population dynamics affect this result?
Population dynamics don't affect the results directly in En-ROADS, in C-ROADS, the model that I just showed you. And that's because it is driven entirely by the pledges. And this is important. We build models towards a purpose. The purpose of this model was to support the international negotiations and build understanding across very diverse players. We are building a second model, which is really an addition to C-ROADS, which is called En-ROADS, that has a different purpose. And there, we're trying to understand dynamics like population. And so what you'll see here, the drivers of the same model has you multiplying population times GDP per capita times energy intensity and carbon intensity. So here, we'll allow you to actually change population scenarios, and you can see the green line way at the left. So what if the UN projection, what if we follow the high projection or the low projection? Karim, other questions?
Yes, when you were working with the Chinese people, with the Chinese academic people on this model, did you get any sense of what kind of commitment China has made to this?
The short version is that China just announced a couple months ago that they're going to declare what year they will cap their emissions. And my understanding is that they have the power to do what it takes to do that. So really what it involves is a huge commitment to energy efficiency and in natural gas as opposed to coal as a way to meet that cap. I'm actually quite impressed by the commitment they have to take action. What we're finding is that they do excellent analysis including system dynamics. So this is a screenshot of a model that we built with Tsinghua University. Over on the far right, you see the emissions from 2000 to 2050 for a variety of scenarios. So they're trying to use system dynamics modeling in order to understand what it's going to take to cap their emissions in different years. The challenge is daunting. They've got so much coal. They've got so many people, and so many people are getting so much wealthier. It is a huge challenge, but they seem to be doing all they can.
Great. What specific policy conclusions come from C-ROADS aside from fewer emissions and more trees?
What a good question. Overall, the short version, just as you all are interested in climate, the main thing that we can say from C-ROADS is that meeting the goals for addressing climate change and reducing climate disruption is going to require peaking global greenhouse gas emissions within the next 10 years and then reducing emissions 3 to 4% annually. And more, less deforestation and more afforestation, which is basically kind of the summary I gave before. Big job, steady work. There are insights that come from En-ROADS about how to do it that I haven't gotten into yet. We'd love to explain more about. We should do another webinar another time about how natural gas is not as powerful a bridge fuel as we thought. How some new technology that's out there that we are hoping for can't save us. We shouldn't be looking for a magic bullet. We should be looking for magic buckshot. That is many, many different actions in energy efficiency, in some sort of way to price carbon, in promoting renewable energy, etc. But those are things I really haven't shown you in the model yet. The key thing with this is it may sound so daunting, capping emissions that soon and reducing it 3 to 4%, but really when you step back, no one thought the Berlin Wall was going to come down. No one thought we would end apartheid as fast as we did or end the violence in Northern Ireland. No one thought that slavery would end as quickly as it did. And there's still some slavery around the world, but at one point, 75% of all people were in bondage in the 1800s. There was it's remarkable how quickly things can change. And that's one message that we believe in because of the powerful reinforcing loops of social change and of industry change that are out there. So that's a little bit of just two of the conclusions that came out of some of our analysis. Others, Karim? Or should I be wrapping up time-wise?
Great, thanks. Yeah, I think we'll wrap up and come back to other questions after we talk about XMILE. There are questions coming about how this ties into XMILE, so let's
Great.
Let's
well, let me
to
just
that.
hit those main points again. As I said at the start, what I hope I've demonstrated to you is how system dynamics can be a powerful method for building learning and action. And action, where people actually change their behavior, change their thinking, that it leads to different investments or different policies as they try to manage these complex systems. And you can see that there's a whole combination of the science of building confidence in a rigorous model, but also the creativity of putting it in a form that speaks to people, and speaks to people in a whole different, wide range of platforms. Around climate change, you know, our insights I just described to you about the urgency, but also the possibility that we can actually pull this off. But also the key thing that XMILE is contributing here is the need for better communications amongst analysts across platforms. So with that, I'll turn it back over to Karim and Steve and really just give another boost to this great idea of XMILE and easing communications across all the important people doing analysis in climate change and in all sorts of other business social issues. So thank you very much. So back over to you, Karim.
Thank you, Drew, for an excellent thank you, Drew, for an excellent presentation. So I'm going to talk about XMILE just a little bit here so we know what it is and we can tie it back. Drew's already done a great job of explaining how it can help. XMILE is a standard that we're developing with OASIS, which deals with a lot of XML type standards. This is an XML format that we're using to help represent models so that multiple vendors and tool providers can share models and actually use models that were developed in other packages. So in the current state of the art today, we have a situation where, shown in this picture, where we have two different software vendors that have developed models, but we can't communicate with these models. And what XMILE does is it creates this XML encoding in between that allows these models to be shared in different packages. And furthermore, it leads to the ability to transport specialized models to other applications and other uses that may not be available otherwise. There are a number of technical benefits to XMILE. I just spoke about sharing pieces, and but we can also archive models over long histories and allow people to access them and be able to run them again. We can reuse common components, so we can build a larger model from components that, from here we have two separate models from different vendors even that can be tied together. It opens up the development to add-on tools for analysis or documentation. It makes system dynamics more accessible to not just more people, but to more applications. It can be embedded in things more easily. For example, we can integrate it with big data applications or with in enterprise applications to make it part of the business process. XMILE also has a number of business benefits directly. The more XMILE models there are, the more revenue can be made from those models because we can apply them to, we can use them in new applications, create new applications that have them embedded or as part of other applications. Increases productivity in building models because we can reuse both whole models or just the components together, and increasing productivity reduces cost, and that with increased revenue increases profits. The XMILE Technical Committee is working from an existing draft right now to try to come up with something in about a year that we hope people can vote on and adopt. We're currently trying to work out what should be in the core system dynamics language. We're wondering things like, for example, should queues be in there? Should conveyors be in there? We just did some work last week adding multiple diagram views to the representation. Before it only had two of them. We've been talking about where display information for model variables go. Does it go with the variables or is it separate? And we're looking for input from people and from help from people. If you'd like to join us either as part of the committee or just to see what's going on, you can go look at the link below, which gives you access to all our all our public documents as well. So how this ties back to Climate Interactive in their model, Drew said something about already, but I was wondering if he had anything he wanted to add beyond that.
No, I think nothing to add. This has been great.
Great, thank you, Drew. So we'll take a few more questions for a few minutes. So one question is about XMILE. Can XMILE translate between SD models, system dynamics models, and discrete event models? And the answer for that in the short term is no. In the longer term, so version 1, we're sticking strictly to system dynamics, but we're hoping there will be a version 2 that then increases the functionality so that we can have discrete event simulation and agent-based modeling as well. The next question is XMILE currently being used with the C-ROADS models? If you want to take that.
So Karim, did you pass the question over to me? I missed that. Like whether C-ROADS is using XMILE?
Yes, sorry. They're asking if XMILE is used with the C-ROADS model at this point.
At this point, it's not, but we'd be open to it.
Great. So let's see. Can XMILE integrate system dynamics and GIS models? So that's another question. And GIS we largely see as metadata added on top of the model to tell you where things are in space so you can create maps of things. So hopefully that metadata will be there. Does XMILE work with iPad? So XMILE is a representation of the model. There needs to be some software that is behind it, and so to the extent that software is available on iPads and software is available on Android machines and Android tablets, and software is available on desktops, and on the web, then you can use XMILE in all those places. And people are working on software in all those arenas. The next question is, who's currently doing exports to XMILE, to the XMILE standard? At this point, the only software that's that's officially writing XMILE is the software from IC Systems, which would be, I think, Instella, although Ventana has a prototype of a tool so they're working on it. That's the state today. I should emphasize, though, that a lot of vendors are, in fact, working on XMILE. There are a number of people on the XMILE committee. You can see at the bottom that Foil is also involved. We've also talked to the people at PowerSim and at AnyLogic. So there are a lot of people who are contributing and who are involved. Next question is, do interfaces transfer with XMILE? So interfaces such as sliders and pictures and buttons, do those translate across? XMILE does include information about all of that, so that does transfer. Drew, if you're still with us, there are a number of questions about what greenhouse gases were included in your model besides CO2.
Great. Let me switch back over. I have a picture that would help people understand that one. Let me pull it up, and I can show you. But maybe it's just more easily verbal. The short version is methane, N2O, the F gases, and then the other Montreal Protocol gases. So we had to go with really all that were considered in most of the other disaggregated models. I can show it on the screen if it would help. So aerosols, black carbon, as well as the F gases.
Great, and there are also a number of questions asking about whether or not this model has been, if it only works at a macro level, or can it be applied regionally or at a community level?
Can the model be applied regionally or at a community level? So the short answer is no. This model can't be applied regionally. But think regionally, you would then want to build another model using system dynamics. And so we've done that with China. We're doing that right now with Brazil. We're doing that with Mexico. Chris Soderquist, another system dynamicist, has built a community model for more of a city or smaller area than a city that then allows you to say, if everybody in the world did what we did in this community, what would that mean for temperature, et cetera? But it's a bit of a stretch to make that kind of leap that everyone else is going to do what you do. So really think of using the same method, but not the same model.
Great, thank you very much. So I'm going to turn it over to Steve Adler to wrap it up for us for today. Here you.
Thanks, Karim. And Drew, thank you for a really fascinating presentation. I think that what you demonstrated is really powerful, how a small group of people with the right knowledge can make a really big difference in the world.
Thank you.
And it isn't every day that you see such a great example and such a passionate team that you put together. And I think you deserve a tremendous amount of credit for what you've done or what you continue to do. And I found your presentation so fascinating. You know, it's really hard for a lot of people to grasp the complexity of the global climate system and the interaction between so many disparate points of view and data points. And it's often that as human beings we're confronted by large complex systems that can't easily be categorized by simple binary yes, no, on or off equations and answers. And in those situations we seek, you know, sound bites and simple solutions, and oftentimes they aren't available, and we make the wrong decision because we're looking for the easy way out. And your model, I think, demonstrates that we can indeed grapple with complex and ambiguous data points and work together to understand how large complex systems interact and how our behavior affects them and how we can change our behavior to affect better outcomes. And I think that's the purpose of system dynamics, is to help us all think beyond just simple cause and effect, binary yes-no situations, and start to realize that every one of our actions has consequences we can see and many unintended consequences we can't see. And if we really want to make better decisions with data, we have to learn to see the world in the complex systems that we interact with and model those systems and run simulations against them to understand what can happen if we make a decision and it's wrong, or what can happen even with the right decision and the unintended consequences of those. And that's really the purpose of this webinar and the webinars that are going to come in the future. We've put together 8 really awesome speakers and presentations to illustrate just how powerful systems thinking and systems dynamics and, in some sense, the language XMILE really can be. In the next webinar, we'll be looking at a healthcare situation from an organization called Rethink Health that have built a fascinating model that helps demonstrate how grassroots community-based health solutions can lead to really important reforms that bubble up to a national level. And I hope you'll be able to join us next time for that one. Following that, we have another webinar a few weeks later on financial services. We'll be looking at, following that, webinars on smarter cities, on big data, on retail, on a variety of other industries as we continue to explore use case examples of how systems thinking and system dynamics are affecting people's lives and really improving business outcomes today, and how these models can benefit from reusable languages like XMILE. I want to thank Drew and Karim and everybody who's worked together so hard to put together this first webinar, and also to the terrific audience that's been with us for this last 50 minutes. You've asked a lot of questions that we haven't been able to get to, but we promise to follow up and get to all of them in email afterwards. These webinars are being recorded. They will be posted to a YouTube channel where you can go and look them up anytime you want to go back and study the material. We hope that this provides an ongoing educational resource for everybody interested in systems thinking, system dynamics, and XMILE. Thanks everyone for joining. Karim, do we have any follow-up questions at the moment?
No, I think that's it, Steve. We're all set.
Good. Would you like to comment anything that I may have missed before we close out?
I think you hit all the points great. We hope everyone can join us in 3 weeks for this next session by Jack Homer, which should be wonderful.
Great. Thanks, everyone. Have a great day.